And yes, it looks weird, doesn't it? I mean, it looks very different. And arguably, at a random glance, it looks longer. It looks like there's more to write.
But the numbers are all small numbers.
The numbers are all smaller, and compare it to actual student work. Often it is shorter because they're guessing things. And don't just look at their work. Look for stuff like over here that looks like this. Because if they had a list of factors that could potentially cancel, who cares what the top does? If it's not a 2, a 5, or a 5, or a 7 in this example, man, you just wasted some time doing some stuff you don't need to do. Not to mention, in algebra, guess how you add fractions? It's perfectly analogous. Every step, every symbol, every dot, every cross off, this example is analogous to the one I just did, and it's the only reasonable solution. Because the only way that I know of to find a least common multiple of two polynomials is by factoring, not by listing multiples. So first step is to factor. So factor that. Hey, what's this missing that that's got? Pretty straightforward. What's this missing that that's got? X plus 1. So I got a typo. I'll fix that. I got a typo. It's supposed to be x plus 1 top and bottom. Okay. What's this missing that that's got? X plus 3. So you guys got handouts now, right? Find that x minus 2 and change it to an x plus 1. I made a typo.
That's all right. We all do it.
You should know this is the first time ever I've made a PowerPoint presentation. And the first point ever I have used Microsoft Equation.
That is very impressive, actually.
So one typo! And I had to use 4 different computers because the 2 I tried first didn't work.
Yeah.
They didn't have the equation in there. Then we factor the top in hopes of finding one of these factors. And in fact, factoring is a lot easier if you've got a good starting place. So if that was a hard trinomial to factor, and you resorted to guessing and checking, what do you guess first?
What's on the bottom?
You guess what's on the bottom. You guess x plus 1 first. And then you guess x plus 2. And then you guess x plus 3. And then if you can't factor it, who cares if it factors a different way? But that's algebra. But it's also arithmetic. And we don't teach arithmetic that way. At least I was never taught that way. And according to my students, all of which spent a lot of time adding fractions, because if they're still adding fractions in their second year of college, you can bet that they've even seen the other method where you find least common denominators from one of my own trained teachers at the university who doesn't buy into this method. Don't tell my boss. She'll figure it out on her own. Hey, most pre-algebra students can do this. They can do the one on the left. I give it for a softball. You know, hey, get this one right on question number 1. What's the difference between that and question number 2? And why can almost none of them do it? I mean, it's the same thing, right? Can you list the factors of 10 and 5? Can you list the factors of 10x? Now, if we don't practice early enough, we do run into a problem. I mean, even my students, even halfway, 3/4 of the way through the semester, I tell them to factor 10x and they write 2 times 10. They simply ignore the x. So those of us that are trying to get students into algebra should teach it earlier and more often in a way that matches their number skills earlier on. Right? Maybe this is too hard, but maybe after we play the what's missing game, we could move into a very simple, do you see the pattern kind of question. We could move into a, not that this is algebra, not that you're doing algebra, but just simply, what's missing at the first what's the first thing missing that the second one has? And can you insert factors in here to make it the same? And then, if it's got the same denominator, write it once. We see this in the textbook all the time. A over C plus B over C is A plus B over C, and everybody skips it. How come you skip that step? For teaching developmental students, students who have seen it before, who don't see the connection, who cannot make the transition from arithmetic to algebra, this is a two-step process. Because what goes in the numerator of this fraction? 5 times 1 is 5, plus 1 times x is x. And are those ever going to go together? So maybe the textbook writers have it right. Maybe this is the goal. Look over what I did on the left. The instant I have a common denominator, I never write it more than once. Now, is it just because I don't clean the bathroom and I don't do dishes that I never do tasks that I have no interest in? Or is there something that the book is saying, written by a math expert, that I'm missing? For example, what's that mean? Right, factors. But what do our students think it means? Multiply the numerators, multiply the denominators. We're setting them up to fail conceptually. And we don't even have to change the questions. We don't even have to change the tasks. We just have to change our presentation. When we think about creating and using analogous tasks, the goal is to build conceptualization ability, and to strengthen student understanding. All right, there's a couple things. Listen here. Don't think my English teacher would like that. But that's all right. Right? Having a student add 2 plus 2 plus 2 equals 8 and hoping they make the jump to the transition to A plus A plus A plus A equals 4A, I think is a little optimistic. Right? To just line up things that look the same in arithmetic and look the same in algebra, I think is overly optimistic. We have to have two things in mind. We have to understand the underlying algebraic structure they're going to be faced with. And especially, I would think, for middle school teachers, that's intimidating or daunting. Right? Because then we have to go back to that question with all the x's in it and at least make a half effort to kind of understand this, and that's daunting. Man, I gotta be honest with you too. When I taught calculus and they made me teach algebra for the first time, I couldn't do that. You know, I had to study, I had to practice, I had to remember how to factor, I had to remember how to do some things. The task must be designed to encourage conceptualization. And to me, at least the experience with my students, this isn't going to do it. And I'm going to leave it cockeyed because it just doesn't work. Right? It just doesn't work. Oh, look, that's what you know how to do in arithmetic. This is what we're going to do in algebra. Right? It just doesn't work. We've got to really go ahead and use that as an idea. If that's what I want to do, that's what I can do. But for my students, I've got to make it painful. Only in the sense of, if you can't force, we got to show them that there's an easier way. And I don't care how many 2's we put there, until we really semi-abstract for them or make the number so large that we need notation to talk about it. Isn't that what algebra is anyway? When the numbers are cumbersome or varying enough that we need notation to talk about it. And I don't necessarily see this in some of the literature that Foshen shared with me. I see some good analogous tasks that fit within about an inch. You know, and I think they need to become cumbersome to the point of, I think my kids, I think my middle schoolers, my elementary schoolers, as in my own children, I don't teach those, not those guys. They would try 42 times 5, and they get the right answer. So could they make this connection? I would hope so. But I don't think they'll see it with smaller examples. And that's really just a pain. That's not tested. But I know that as I try and teach exponent rules to my college students, this example doesn't really work. It does for some of the class. It really does. They see the connection, they get it, they learn the pattern. But for a lot of cases, they really end up coming to my office for help later, and I just start putting ones before and after things until they're forced to think about conceptualizing the task. Because I watch their fingers, and they hide them almost as well as I did during this lecture, right? They count, and they don't try and make the jump. They think they can answer it just by counting. Of course, the problem with abstraction then is overgeneralization. The instant they learn this rule, and what's the rule here? What do we do with these exponents? Did I go too fast? We multiply them. Then instantly you give them this question, and what do? They multiply them. So as soon as we teach a conceptual task, we instantly have to be aware of where common misconceptions are, and at least test for the misconceptions. I'm not saying give them leading questions, you know, like are these the same or different? I don't know, but we need to be at least aware of. And I think we all are, because this is what students are famous for, right? Once they learn a rule, they use it for everything. Then they learn a new rule and they use it for everything. And then they can't, it doesn't matter how good they did before, they can't go back and forth. And of course, algebra is full of things that we think we understand and we don't, both as teachers and as students. And I've had teachers think that the absolute value of negative x was x, especially ones that had not ever taught algebra. So to make that jump ahead to algebra, especially for the middle school teachers, be cautious. Look it up. Don't use the internet, because I've had some bad luck this year using the internet to help my students. It's a little overgeneralized, not very specific, and can lead to misunderstandings. Like absolute values make things positive. I've seen that in print. Is it true that absolute values make things positive? No, it's not. It could be non-negative. It could even appear to have a sign, right? I mean, algebra is hard. Let's acknowledge that to our students. Give them hard examples. That this is a true statement. If x is negative. So let's not gloss it over that just by doing this, everything's going to be easy. There are things about algebra that you cannot understand without careful study, especially anything notational. And so those little dots, as opposed to parentheses, in my presentation, at least the way I wrote them, there's a difference there. Difference between factoring and multiplying, in a way that could help or hinder our students as they move forward in algebra.